Hello, welcome everyone to the spring 2021 semester, and welcome to the electronic devices course. So the format of this course is asynchronous, as we some of the details I mentioned in my email that was sent yesterday. Also, the outline is on Sakai. So please go through the outline to see more details on the exam, quizzes, grading, policy, and always feel free to send me an email if you have any questions. Uh, you can always reach out to me at umar.hassan@rutgers.edu. Okay, so there are 14 weeks in the semester, and I will upload the lecture recordings every week. And whenever I will upload the lecture recording, I will send you an email so you will know that the lecture recording has been uploaded. One advice will be to please don't wait till the last minute and go through these lecture recordings at your convenience, but soon as well. Yeah, and the good thing about the asynchronous mode is since the recordings are always there, so you can watch it multiple times. So if some of the concepts are not clear, you can watch it multiple times, or also always feel free to send me an email. Okay, so there are multiple chapters that we are going to cover from the book Satter and Smith, Microelectronic Devices. Chapter number 1 on introduction of the amplifiers. Chapter 2 is on operational amplifiers. We're gonna cover next chapter number 4 on diodes. Then our that will be around first half of our semester, and then the rest of the 7 weeks we are going to talk more about transistors. Very important topic. uh, we are gonna cover two of the most commonly used transistors that are commonly used in industry to make microprocessors and a bunch of other electronic circuits. And those transistors include MOSFETs and VTCs. Anyways, we're gonna cover in detail about all the topics. So this is our first lecture. So let's start our lecture today. So we are going to start with we are going to start with chapter number 1 from the book, and we are going to majorly talk about signal amplifiers in this chapter. So let's start with this question. If you would be in that class, I would have asked you. I guess now I just need to give you an answer. So why do we need signal amplification? Right? So what does these signal amplifiers do? They amplify a signal. So the question comes, why do we need signal amplification in the first place? So I guess you probably know some of the answer to this when I ask this question to most of the students in the live sessions. Mostly they give me an answer. For example, you are listening to a music and you want to amplify that, especially if you want your neighbors to hear about it. That could be one of the examples that we want to amplify the music, right? We have speakers. Essentially, what they are doing is amplifying the signal. Another kind of a nerdy example could be, for example, if you have built some sort of an instrument, an electronic circuit, an instrument that is producing very small changes in the electrical signal. For example, and this is kind of related to my research as well, here is a microfluidic channel. The dimensions of this channel is 20 microns. 1 micron is 10 to the minus 6 meters. Okay, let's say this is the height of the channel, right? And you have these very small electrodes in this channel. Somehow, we're not going into the details of how. And then you have a biological cell, a white blood cell, right? So this is a white blood cell of our body. as it is going to pass over these electrodes, and if we apply an electrical signal to these electrodes, as it will flow over these electrodes, it is going to disrupt these electric field lines. It is going to produce this very miniaturized changes in the electric current, which we can pass it through the resistors to convert them into the voltage signals. So essentially what we are getting is a very, very minuscule changes in the voltage values. Right? And if I have to reliably process that signal, or essentially in this specific example, if I want to detect the presence of the white blood cell, whether this white blood cell passed over the electrodes or not, I would need to amplify the signal. Coming back again, signal amplification, super important, right? So for example, in this experiment, we generate microvolts. We need amplification of the signal to reliably process / in this specific case detect cells here. Right, so that is why signal amplification is so critical. Okay, so let's write the equation for signal amplification, right? I'm not going to talk about this thing more. It was just to give you an example. Okay, so let's talk. What is the equation for the signal amplification? Signal amplification, if I have to write a signal amplification equation, it should have two things: input and output, and some sort of an amplification factor. So let us suppose that you have. Okay, so let me write the right hand side first, where you have an input signal, right? So this is my time dependent input signal, voltage signal. I would amplify it by a factor, let's call the factor A, and what I will get is the output time dependent output signal, right? So what is A? So this is the equation for the amplifier. So A is my amplification factor. It can also be called as a amplifier gain. Okay, great. All right, so now we are going to, so this is amplifier, right? So what we want to amplify is we want to amplify our input signal, right? And we want to amplify our input signal by a factor A. So let's talk about this factor A in more detail and what sort of amplification that we want. So there is another very important concept that is, so you're gonna realize that in the entire course, I'm gonna kind of put a lot of emphasis on the concepts. Very, very important. Right, we are going to do a lot of these circuit problems and examples as well, but the concepts are important, so I'm going to put a lot of emphasis over there, and your quizzes, exams, midterms, and the final exams are also going to reflect those conceptual questions and understanding of these topics. Okay, so the next thing that we want to talk about now is linear amplification. What I want is linear amplification. Okay, so what exactly is linear amplification? Linear amplification means that whatever we want to amplify our signal, input signal, I want the amplification to be a linear, or I want my amplifier to behave as a linear amplifier. What does that mean? Let's look at the equation again, right? So this was my equation, A V I of t, right? Okay, now let's look at this equation again. Let's say 2A, or whatever that is. Okay, so A can be 2 times the okay, over here for example, A can be 2, 3, 4, 5. It could be even 2 point something. Anyways, V naught of t. Now let the amplification to be V A square of Vi of t. Right, so what exactly is, so can we get, so the idea was that can we get the higher powers of amplification or not? Or what does it mean by to have a linear amplifier? So the linear amplifier means that I want my signal to be amplified, but only linearly and not linearly. I think probably let me put some of the graphs to have a easier understanding. Okay. So let's see if I have to express this equation over here. This is my V naught, this is my VI, and for example, this is, right? So this is a linear line, right? And the slope of this line is A because V naught equals AVI, right? So the slope of this line is A. If my V naught is exactly equal to VI, this means that my A equals to 1, then my line would be equals to exactly in the middle, right? So this would be when my gain equals to 1. This means that no amplification is happening. Whatever my input is, that is equals to output here, right? So this comes over here. So interestingly, if you look at this graph, okay, I'm going to come back to this equation and higher powers of the amplification again as well. I think that will clear up more the concept more. Okay. All right. So we want this amplification or this line to be linear. For example, how a nonlinear plot is going to look like over here, or how the nonlinear amplification is going to look like. It may look like this. Right? So this is more like an exponential graph, right? So what is happening over here is that the small changes in the input signal are being amplified by a certain factor, but the bigger changes in the input signature VI are amplified exponentially, right? So this is what we want. We want our amplification to be linear so that all the signal information is amplified and no new information is added, right? So what we want to do is in linear amplification, okay, so what's sorry about that. Okay, so what we want to do is we want our all signal information must be amplified. Currently I'm neglecting the noise. Second important thing is that no new information is added. No new information must be added, right? So this is the concept of linear amplification. We want to amplify everything in the signal in exactly the same way, and that will result in preserving the waveform. For example, if I have a sinusoid, I want to preserve the sinusoid, right? I want to preserve the waveform. Okay, so let's look at amplifier. I wanna discuss one more concept here before we go away. So let me the difference in between an amplifier and attenuator. Okay, so amplifier versus attenuator. So I'm going to make two plots here, and I would have asked you this question in the class and cannot ask you this question over here, but what do you guys think? Which of this is a linear amplifier? Second, which one is an amplifier and which one is an attenuator, and why? Right, so I tried to draw both the lines, both of these voltage relationships in between input and the output with the straight lines. So at least I tried to make it to look like a linear relationship. So both of them plots, both A and B are linear. A and B are linear amplifiers, right? Or at least they represent a linear amplifier. Second, if I look closely, which one is an amplifier and which one is an attenuator? So if I look closely, I know that this signature is V naught over VI, which means that nothing is being amplified at this dotted line. So anything above And the slope of this transfer characteristics is represented by A, which is amplifier gain. So anything that is above this dotted line means that signal is being amplified. Anything below this dotted line means that signal is being attenuated. Right? So this means that A is greater than 1. Over here, this means that A is less than 1. Right? So your A is an amplifier, A is greater than 1. Your B is an attenuator, A is less than 1. Okay, great. Now let's consider one more important concept before we move on, and that has to do with what if A equals minus 1, right? So your V naught of t equals minus 1 Vi of t, right? Is that an amplifier? Oh, yeah. So amplifier means A should be greater than 1. So let's make it 2, minus 2 and minus 2. Okay, to make things simple. Okay. So if we have A equals minus 2, so is that an amplifier or attenuator? Again, I would have asked you this question in the class, and now I can just give you an answer here. So whenever you see a negative sign with the amplifier gain, this does not mean that it is attenuating. Because the negative sign over here is that means that the signal is being 180 degree out of phase. The signal is still being amplified by a factor of 2. Right? So amplification factor is still 2. So your amplification is still happening by a factor of 2. The negative sign indicates that it is being 180 degree out of phase. Right? So amplification by a factor of 2, and negative sign shows 180 degree out of phase output. Right? Okay. So for example, if you give a sine wave, it will be 180 degree out of phase and multiplied by 2. Okay, great. Now let's talk more about the amplifier. So a major portion of the course is again going to talk about the amplifiers, and in this chapter we are just giving you some very rudimentary and basic concept about amplifiers. We are discussing it in kind of very briefly, but also very simplistically, and we are going to advance more later in the chapter, and especially in the next chapter when we are going to talk about one of the most commonly amplifier that is used in electronic circuits called as an operational amplifier. So we're going to talk about that in the next chapter. Okay, so anyhow, let's talk more about it. So what is the symbol of an amplifier? Circuit symbol of an amplifier. I will try to, sorry about my writing if you don't understand. So that is why I'm kind of saying these words again and again, and I hope that that should make up for it to a certain extent. Okay, so what is a circuit symbol of an amplifier, right? So circuit symbol of an amplifier, again, very simplistically, looks something like this, right? So here is your input signal, here is your output signal. If you look closely, this looks like a 2-port network. 2 characteristics of these 2 ports, for example, right? So this has 2 ports, right? So this has 2 ports. One port is an input port and output port, right? So this is one of the ports and this is the second port, input and output port. Second, if you look at this triangular symbol, so this triangle, so this triangle, so this indicates the direction of the signal flow, right? Indicates direction of signal flow. Interestingly, you are also going to come across this multiple times throughout the course. Whenever we are representing amplifiers, commonly amplifier can also be represented with a circuit ground, and especially when the ground is common in between input and the output. Again, this is your output, this is your input, this is amplifier A with a gain A. And now this is again a common circuit ground in between an input and output. So this just represents common ground between input and output. Okay, great. So let's talk more about another important concept. So we have introduced this word amplifier gain. That's a thing that I was talking about, right? So earlier, if I will go back here in the first slide, okay, yeah. So over here, you can see that. What is this A? We introduced this thing as an amplifier gain. So what is this A? This A equals V naught over VI, right? So this was a factor, amplification factor by which the input is being amplified or multiplied here. So now we are going to discuss this thing in slightly more detail. So if I am amplifying a voltage, I will like to call this factor as a voltage gain. Okay, so let's discuss the voltage gain in slightly more detail. So suppose we have a voltage linear amplifier which is fed with input signal Vi of t, and it provides output V naught of t across load resistor RL. So I can draw a circuit based on this statement, right? So essentially what we have is a linear amplifier here. So I can draw amplifier symbol. And then, so this was a symbol that we talked about. Okay, so this is an amplifier. This amplifier is fed with the input signal Vi of t. Okay, so I ended up connecting this Vi of t here. Right, so this is our input signal going here, and then it is connected to the load resistance RL, and the potential drop across the load resistance will be the output V naught of t. So the current going in would be equals to II, input current, and so this is the input current that is drawn from the source, and then the output will be equals to I naught, that is delivered to the load. So in this circuit, the voltage gain here, so the voltage gain, right? Now I am going to call that as an AV, right? So we introduce this equation V naught of t equals AVI of t, right? So I'm going to call that with a subscript V, which means that this is what we are talking about is a voltage gain. So the voltage gain AV equals V naught over VI. What are the units? V over V, right? So it's a dimensionless number. Okay, so again, since we assume that it's a linear amplifier or our factor A, V, this is a linear parameter. So this means that, for example, if our input is a sine wave, our output is a sinusoid wave as well, right? So waveform preservation. waveform preservation, simplistically, in simple terms. Okay, so let's do one more thing here. As I have told you, we can represent a linear amplifier by this plot, right? So over here, this is your VI, this is your V naught, and the slope of this line is the voltage gain factor, AV. All right. So these characteristics in between the input voltage and the output voltage are also known as, or are commonly known as, voltage transfer characteristics. Voltage transfer characteristics of an amplifier. You are going to come across this term again and again, multiple times throughout the course. So I hope that whenever you see the word VTC, also sometimes abbreviated by this, VTC, which means that voltage transfer characteristic, and essentially it means that we are showing the relationship in between the input voltage signal and the output voltage signal. And this linear line over here shows a linear amplification. I think I've kind of very mistakenly almost drawn it when A is almost equals to 1, but again, yeah. Ideally, it should be even higher, something like that. Okay. So anyways, so these could have, for example, you can draw multiple lines here to have different amplification factors. Okay. So anyways. All right. So let's talk about, we are still talking about the gains. Let's talk about, so we just talked about a gain. Again, our circuit will remain the same. In this linear amplifier circuit, we connected the circuit to the input voltage, VI of t. II is the current drawn from the source, and it has a load resistance attached at the output. And the output voltage is V naught of t. Okay. So now let's talk about the other gain factors. Right now we have just introduced the gain, which is what we have called as a voltage gain. Now we are going to talk about the power gain and the current gain. Power gain and current gain. Okay. So in terms of a power gain, so for a voltage gain, we talked about that the output voltage is higher than the input voltage. So in terms of a power gain, our amplifier will provide higher power to the load compared to what is drawn from the source, right? So it needs to increase the power. So in very simple terms, we can define the power gain. Again, power gain, we can represent the gain by A, and subscript P shows power gain. We can easily call it as a output power or a load power. Output load power to the input power, right? Similarly, we know for the voltage gain, it was output voltage to the input voltage, power gain, output power to the input power, right? So we can also call as a PL, load power, PI, input power. Okay. We can also write down further the load power equals to output voltage and the output current, input voltage and the input current. All right. So and we can also write I naught. So what is I naught here? I naught equals V naught over RL, or it is the current which is delivered to the load. It is current delivered to the load. And what was II? II was the current which is drawn from the source. So considering this, we can also write down the equation for the current gain, right? So the current gain is AI. AI now, again, I is a subscript for current, and A is a gain parameter, so it's a current gain. So current gain is output current over input current. And the units, dimensionless number, units are amperes over amperes. Over here, sorry, I forgot to write over here. This is watts over watts. Okay, so this is good. Now, if you look closely in between, so this is the current gain, I naught over II. If we go back to the voltage gain, our voltage gain is V naught over VI. So considering this, if I go back and look at this equation again, I can easily split this thing. AP equals V naught over VI into I naught over II. V naught over VI is the voltage gain, and I naught over II is the current gain. So you can write the power gain is a product of the voltage gain into the current gain. Okay, great. We have one more small concept to talk about, and before we end our lecture today, and then we are going to discuss more topics, and in the next lecture we're also going to do one example that will help clear up these concepts more. Okay, so our last topic for today is how we can express these gains in decibels, right? So expressing gains in decibels, right? So usually our gain numbers are very, very larger, right? Like 10, 100, 1,000, or even more. For example, if my input signal is very, very small, let's say in microvolts, and I ended up amplifying it to a 1 volt, I am talking about amplification factor of 1 mega 10 to the 6. Since our amplification numbers are very, very higher, so engineers like to make the thing simpler for representation, for writing. So they introduce this term decibels. Yeah, we would like to express this, not introduce. We would like to express, and kind of like to express this thing in the terms of decibels. So essentially what decibels is, we ended up multiplying our gain parameters with the log functions. Okay, so I am going to write down these expressions. So the voltage gain in decibels equals 20 log of AV decibels. Current gain in decibels equals 20 log of AI into decibels, and power gain in decibels equals 10 log of AP into decibels. Okay. All right. So if you look at these expressions, our voltage and the current gains are 20 log of the gains, and our power gain is 10 log of the gain. So why is that? Earlier I would have given you that as a homework to look at, but very quickly I can kind of tell you, because you can very easily start from one and develop the other. For example, I can do a quick thing, right? Our power gain dB is 10 log of AP, right? So it is 10 log of AP. So what is AP? Our AP is V naught square over RL over VI square over RI. right? So if our input impedance and output impedance are over here, if our input and the output impedances will match, then we can express this thing as, right, so this will match with this, and we can express this thing as 10 log of v naught squared over vi squared. So you can take this 2 thing out, so 2 will, sorry, 10, just call this gain factor, right? So we start with the voltage gain, and then v naught over vi square, so it will come out to be a 20 log of v naught over vi. So starting with one expression, you ended up kind of developing the other expression. However, please make sure that these expressions has an inherent assumption built in which our input and the output impedances are the same. Okay, there's one minor, one important thing, but a quick concept, and before we will end our lecture today. So the last thing is, again, I kind of hinted that previously, that whenever a gain has a negative sign, right, if our voltage gain has a negative sign, this means more amplification is 2, and negative sign means 180-degree phase shift of output, phase shift of input, right? So our input will be phase shifted. Okay, so what does this mean? And the second important thing that we talked about is the only way we will get an attenuation is when our voltage gains are, for example, 0.1, 0.2, or less than 1, but not negative, right? So then we get attenuation. Attenuation when AV is less than 1, in between 0 and 1. Yeah, let's call it like that. In between -1 and 1. Okay, so importantly, if your voltage gain, let's say AV is, however, decibels, if your voltage gain is -20 dB, what does that mean? Is that an inversion or an attenuation? Please do note that minus, when it comes to, so this is the absolute values and not the dB values. However, when you are going to write this thing as a dB in dBs, things will get inverted. For example, if your voltage gain is -20 dB, this means that signal is attenuating by a factor of 10, right? So let's prove it. For example, if my voltage gain is 0.1, right? So this was when I was talking about, essentially, more realistically, it should be somewhere between -1 to 1. So this should be an attenuator. So anyways, when our voltage gain is 0.1, so let's express that in dBs. So this means that in terms of dB, so this was the absolute numbers. In terms of dB, it will be 20 log of 0.1. If I will solve 20 log of 0.1, it will come out to be -20 dB, because log of 0.1 equals -1, right? So if you see a voltage gain as an absolute value, not with the dB, then the negative sign means it is inverted. It is 180-degree out of phase. However, if you see it with the decibel like this means that your signal is being attenuated. So please, I hope that this entire explanation has made this concept more clear, because such questions may appear in exams and the quizzes, and I hope you understand this basic concept. Okay, so with that, I will end our lecture today. And in the next lecture, we are going to discuss in more details about the concepts of power. We are also going to talk about more about the this voltage transfer characteristics, or some other concept related to saturation. Okay. So with that, I will definitely upload this video to the website, and I will let you know. All right. With that, thank you so much, and I hope you have learned something out of this video. All right. Thank you. Bye bye. Have a good day.